so on Wednesday, we were at the H bridge. Okay, more BJTs. So it looks like this. I have a transistor like this, and then another one here. Ground it. And in the middle, I have a motor here, DC motor. Remember the motor driver you used? There's a digital control. So there are two pins to control the direction of the motor. And if you give a plus minus or minus plus, it's going to give you it's going to rotate in a different direction, clockwise or counterclockwise. So here's how to implement it. So before we look at this circuit, let's find out what is this. The symbol looks different from this transistor we just covered this week. This is called a PNP transistor. It's a PNP junction. Operates really similar to the NPN. So PNP transistor is a counterpart of the NPN transistor. So what you want to do is to open it up is forward bias this PN junction, which makes sense. And here's B, here's E, here's C. And get another one here. So that's a PNP transistor. Here's E, here's B, here's C. And the current flows like this. A tiny current and then a larger current like this. But in your NPN transistor, keep in mind, whenever you see an arrow here, that is showing you where the emitter is, right? So here's the emitter, here's the emitter. This is NPN, this is PNP. And the current here for the NPN, remember, is there's a little current flows into the base, and there's a larger current flows in the collector, into the collector, and merges at the emitter, so you get a larger current. But here it's different. You got two branches, goes out from the base, and then flow from the emitter to the collector. It doesn't need to know all the details of the physics. It's just like, let's look at this kind of configuration. If you are trying to get the current flows in this way, and you kind of know that you want to forward bias this guy and forward bias this guy as well, because you want to give a pressure from the top to bottom. So the current flows from here, a little current getting to the PNP junction, and there will be a larger current flow through the emitter. So this goes to here. So the emitter's current, part of it goes to the base, and part of it goes to the collector. All right. So why do we need a PNP? If we have NPN, which works pretty well, why do we need a? It's a similar concept when you need both the PMOS and NMOS. So if you look at the PMOS, NMOS and PMOS, here's the NMOS. The reason we need the NMOS is the NMOSes are good at pulling the voltage down to the ground. Why is that? So this is a better configuration to pull the output voltage to the ground. For example, this is 10K is pull up resistor. If you want to pull the output to the ground, the NMOS can do the job. However, PMOS cannot do it well. I'm going to explain pretty soon. So if I open this up, if this is high, what's going to happen? If this is high, the gate is high for the NMOS. So high means it's a VDD, and we know that we need to turn on VGS, which has to be larger than VTH in order to turn it on. And now we have VDD. Definitely this is on, right? So I'm going to pull this to the ground. So this will be very close to GND, and you can consider that as a GND. So if you turn it on, you get 0 volts. If you turn it off, no current flows through this channel, no voltage drop across the 10K. What's the output? What is the output? If you have this NMOS to be off, if you turn it off, what's going to happen for the output? No current. What's the output? What's the output? Come on, guys. You guys are better than that. VDD, because no current, no voltage drop. Whatever here is going to be whatever here. If I turn it on, this will be pulled to the ground. You are thinking, hey, this is being turned on. You got a channel here, and you have VDD here and ground here. Why is not VDD? Why is ground? The first 2 weeks, the circuit one problem. Why? Yeah, I mean, if I turn it on, right? The electrons are willing to go to the either way, so this is being shorted to the ground. The proud resistor is giving a resistance to the VDD, to that path, right? So this is 0. So this performs like an inverter. In the old days, if you do not have the PMOS, when PMOS was not being used in the CMOS chips ICs, people use the NMOS logic like this to form an inverter. Okay. So the NMOS is pretty good at pulling this output to the ground, which works pretty fine. It's not working really good to pull the output to VDD. Why is that? If I want to pull this to VDD, if I want to turn it on and pull this guy, here's out. If I want to pull this output to VDD, is that possible? And what should I do? If the input is 0, what's going to happen? The transistor is off. So what is the output? Ground, because no current, no voltage drop, 0, 0, right? If I turn it on, connect this to VDD, what's going to happen? I'm trying to turn this on, right? And I want to pull this to VDD. But will that happen? Would that happen? So think about it. If you turn this on, right? VDD, for example. And I'm trying to get this one being pulled to VDD. So for example, I got a VDD here. What's going to happen? Look at VGS. What is VGS as this case? What is VGS? If I have VDD here, it won't happen. But if I have a VDD here, what is VGS? VDD, what is VGS? Come on. What is VGS? 0. Is it larger than VTH or smaller than VTH? Smaller. So it's going to be off. So that won't happen. What's going to happen is the largest value you can get from the output will be this. And that's the largest you can get. So for the 1 micron technology, VTH is like 0.8 volts. Okay, so can you pull this straight up to VDD? No, it's going to be like 4.2 volts as the maximum. So the NMOS is not good at, sorry, we're not using this, so that's fine. So the NMOS is not good at pulling the output to the VDD, but it's good at pulling the output to the ground. That's why we need both NMOS and PMOS. But the NMOSs are always, during the labs, when you are doing the layout, So all the NMOSes are at the bottom, being shorted to the bottom rail, which is the ground rail. Remember? All the PMOSes, like the inverters and all the NAND gates are, so they have the NMOSes at the bottom, and the PMOSes, all the PMOSes are in the NWELs at the top. That's why you need a both, not just NMOS or just PMOS. Now let's look at the PMOS. So normally this is S, this is G, this is D. For this configuration, we have an output here. Question is, can you pull out the output voltage to VDD? Just 10K is pull down resistor. Can you pull V out to VDD? And when is going to happen? Similar. So how do you turn on this PMOS? Remember? So for NMOS, you need a positive VGS, which is larger than VTH to turn it on, right? For PMOS, you need a VSG. It's very similar. You need a VSG to be larger than VTHP to turn it on. After turning it on, just give a pressure to here, then the current is going to flow. After this is turned on, you just give a pressure, the current will flow, right? Very similar. So that's how you turn it on. You have to have a VSG, source to gate voltage, larger than VTHP, which is normally 0.9 volts for the 1 micron technology we used. All right, for this case, S and G, how can you turn it on? Turn the channel on. How? Grounded. So it's on. Can you pull this up to VDD? When it's on, you are saying, hey, if this is VDD, then there's no pressure, no current flow. It can be very close to VDD. So this actually works. Okay, so you can pull out up to VDD in this case. So you can see that PMOS are pretty good at pulling out to VDD. It works pretty well. Can you use PMOS to pull it down to the ground? Sounds like not. C. So can you pull this voltage terminal to the ground? If you turn on this channel, can you just pull it to the ground? So do you need what's the voltage do you need for the gate? So you want to pull it to the ground, at least you have to turn it on first, right? So you need this one to be wait. Yeah, can you do that? If you ground it, can you pull it to the ground? So let's assume I can pull this to the ground after I turn it on. And you have a VSG here is what? 0. So it should be off. So actually cannot turn it on. Right? So the lowest voltage here will be what? VTHP. It has to be larger than VTHP or equal or larger than equal to or larger than VTHP to turn it on. So the lowest value will be VTHP. So it actually drops from VDD, you know, and whenever it reaches VTHP, it's going to stop. So you are measuring the output. This VTHP is like 0.9 volts. Oh my goodness, it's way higher than ground. I want to pull it down to ground, but I cannot. Right? It's the same concept as your BJTs. So you need both the PNP and NPN. Why? Because you want to turn it on here. So you can pull this point to VDD, and you want to turn it on here to pull this point to the ground. So why do we need this kind of H bridge to drive the motor like this? Since we want to control the rotation direction, clockwise, counterclockwise, depends on the polarity of these two terminals, plus minus or plus minus like this. How? So think about this, the combination of AB, if AB is 0, 0, what's going to happen? 0, 0. So to turn on the PNP, I need the base to be low, right? So I need a 0 to the base for PNP. But for NPN, I need the base to be high to turn it on. So if I have a 0, 0 for AB, what's going to happen? Which is on, which is off? 0, 0, which is on, which is off? These two PNPs are on, and these two NPNs are off. Are there any current flow? No. What about this? 1, 1. So one can, top twos are off. Bottom twos are on. Still no current flow. Is these two transistors blocking the current from VDD? It's no current flow. So what if I have this? 1, 0. So 1 here is going to turn on this guy, and 0 here is going to turn on this guy. So the current is going to flow like this. Do we have a circuit? You have a loop. Yes. It's going back to the ground, to the end, to the cathode of the battery. So it's plus minus. It's case 1. If AB is 0, 1, what's going to happen? 0, 1. 0. On, off. 1. On, off. So current flow in this direction, in the opposite direction. So it's plus minus, case 2. So you can see the current flow, the direction of the current flow has been changed based on the digital code you gave to the H bridge, the motor driver. That's how that works. So what's the name of the driver? You still remember that? Like L293L, something like that. In circuit 1 you used. So there are 2 pins. You can control the direction of the motor. You can give a 1001 to control the direction of the motor. That's how that works. That making sense? But at least you understand why do you need a PMOS to pull everything to the VDD, to the top rail, and you need the NMOS to pull everything to the bottom rail. So you're going to use it a lot in the labs. Since all the NMOSes are at the bottom, but you have never thought about why you need both. That's why. And another application for using, so that's actually the major application of using BJTs, is amplifiers. We're not going to do any small signal analysis. That takes like 3 weeks or 4 weeks to cover. We're just going to look at the bigger picture of using BJT transistors, how to build a amplifier, and mainly the DC points, DC quiescent points, Q point. It's DC biasing points of the BJTs. But let's take a look at what the BJT amplifier looks like. Amplifier. So here's for example, this is audio amplifier. Where's the output? Here. Here's a speaker. Okay. So these 2 resistors will bias at a certain Q point. We're going to cover what is a Q point pretty soon. Because this is a voltage divider, you can control these two resistors, the ratio of these two resistors, to give a DC voltage here. So you can bias it at a certain level, so you have rooms from at the top and bottom to swing that small signal. So here's the signal. That's an audio signal, for example, in millivolts. I can amplify it through here. So the signal is going to swing here, and you're getting an output. So this capacitor is a high-pass filter. It's going to filter out all the DC offside and only amplify the signal itself, but not the DC offside. And then you can feed it to the speaker. Okay, that's a very typical application for of using BJTs. There is a question: why you can amplify the signal by using this guy? So I have to look at the curve. VBE, IC. What that looks like, the IV curve for VB and IC for the BJT, for the NPN. Similar to the NMOS, right? It's gonna increase exponentially after it reaches the threshold voltage, which is somewhere around 0.7 volts. After it's turned on, it's gonna look like this. And you hope this can be as steep as possible. Why? So you want to amplify the signal. You want to amplify IC. Why I want to amplify IC? Because if you amplify IC, the current flows through this resistor will be amplified. And according to Ohm's law, current times resistor will be the voltage. Higher current, higher voltage. Okay, higher voltage, you get a big signal change at the output. So now, if you look at the VBE, if you change the VBE slightly, that's why I hope this one to be steep. Imagine if you change VBE in this range. Here's the VBE swing range, right? You swing the VBE in this range. How VC will be changed in this range. You swing VBE here, but your IC is swing here. Right? I hope this can be as steep as possible so you can amplify the signal. A tiny swing will give you a huge swing as the output for IC. So IC swing like this. You got a small swing here, like a large swing here, so it's being amplified. Okay. Because of V and I, the V and I follow this curve, has to run along this curve. So that's why you swing here, you got an output swing, which is bigger. That's how it's getting amplified. Okay. Here's a pretty popular amplifier called Darlington's amplifier, or just Darlington amplifier. So it has different stages. If you look at the 741's op-amp in the circuit, you can see there are a couple of Darlington's amplifiers in there in the IC. It's pretty simple. Let's see how that works. For example, here's the output. Remember, IC equals to beta times IB. So the IB from the first stage is being amplified by beta times, and that IC is being used as the base current for the second stage. So what's the current here? If they have the same beta. So the first stage amplifies the signal by beta times. And I use that signal as an input current for the second stage. And that will be amplified by beta times again. So what's the current here? Right? And get a larger gain. NPN BJT. The IS equals to 10 to the negative 15 amps. And beta is 100. And the circuit looks like this. Here's a current source. $5 volts, 3K ohms. And this is 10 microamps. So the question is, what is VBE and what is VCE? VCE. One, what is VBE and VCE? That's the first question. What is VBE and VCE? So IB is given, beta is given, and you can find out IC, just beta times IB, right? And because you know IC, so you know the voltage drop across this resistor, just use 5 volts minus IC times 3K, you got VCE, right? So what about VBE? I know it's close to 0.7 volts, right? But since this is asking you what is VBE, and we know that the transistor is being turned on pretty much in a range of 0.5 to 0.7, right? I know it's pretty close to 0.7, so I can expect the result will be somewhere around 0.7. You cannot just directly put 0.7 here. You have to calculate it. So what's the equation to calculate VBE? So I introduced the equation for IC last time on Wednesday. So IC equals to IS times VBE over VT. So VT is a thermal voltage, which is 25 millivolts at room temp. IS is given. It's proportional to the junction cross-sectional area and the temperature and all these other things. So this is constant. It's not being controlled by anything. It's constant. It's a saturation current. And it's given. So if, let's just do the calculation really quick. So what is VCE first? What is VCE? What's the equation to calculate VCE? VCE here, the collector emitter voltage drop equals to 5 volts minus the voltage drop across the RC. So VC equals to 5 volts minus IC times RC. And you know IC is beta times IB. And you know beta is 100, and you know IB is 10 microamps. So just after get IC, plug it in here, and you know RC is given, which is 3K. So you can find out VCE easily for the first question. And the second question, no, still the first question, but another one. VBE, what is VBE? So IC equals to IS times E VBE over VT. So you know that E VBE over VT equals to IC over IS, natural log on both sides. You're getting VBE over VT equals to natural log IC over IS. So VBE equals to VT times natural log IC over IS. So IS is given. IC has been calculated here. And VT is 25 millivolts at room temp. I will never use a different value, so it's 25 millivolts forever. Why? Because the US is the first is the first, how to say that, first world country, except for Texas, right? The room temp can be different, but here in Colorado, we're fine since we have winter, we have snow every year, so we are ready. 25 millivolts for room temp, right? Can you calculate for VBE for all these given conditions? Are ready? Yeah? Anything is missing? Nope. You just need a calculator. Search in Google, natural log calculator, just put in the numbers there and find VBE out of it. Any questions? All right. And the second question is, replace the 10 microamp current source with a resistor, a base resistor, and a voltage source, which is 5 volts. So what resistance is required? To result in the same operation. What does that mean, the same operation? The same operation means you bias this NPN transistor at the same level. So have the same IC, same IB, same VCE, all this kind of stuff, right? So it's at the same point on the IV curve. It's going to move all the way. You can move it. You can set it up at anywhere. But the same operation means it's being biased here specifically, right? So if you have an exact or specific VBE here, and you put in here, you got a specific IC. You have an IC, and you put in here, you got a specific VCE. So all the DC points are set up. Right? So that's how you operate it at a certain point. So if you're not changing this operation point, then that means you have the same IC, same VB, IB, VCE, VB. So all the DC points are fixed. You're not changing it. So now I'm going to replace. So this question is asking you to replace this current source and replace it with a voltage source, which is 5 volts, and a resistor, a base resistor here. So that looks like this. 5 volts, 3K. Here's a voltage source, which is 5 volts. So what is this? R, you need to give the same IB, same IC, same VC, same VB. And as you know, if you can find out, if you can get the same IB, you're done. You don't have to find out all the same values. If you got same IB, and IC will be beta times IB, so IC is fixed. And the voltage drop across this resistor is fixed. And VC is fixed. Not clear? You just need to fix one, right? So what is IB here? What is IB here? 10 microamps. So I need this guy to be 10 microamps. So actually, I don't know the. Okay, yeah. So the RC is fixed. And what was the VBE? What's the VBE? Because you want this NPN to be operated at the same point. So the VBE you calculated here will be used here. All right. So VBE was calculated just now, right? In the first question, I already answered that question, so I know VBE. So what's the voltage across this resistor though? If I have a RB resistor here to protect the base, so it's not being blown up. So I just use the 5 volts minus VBE over R. That should be what? That should be what? 10 microamps. Can you calculate for R here? Right, so RB can be calculated. So if you know RB, you're done, because this is asking you what is the resistance. What resistance is required to result in the same operation. And it's not asking you to change the RC at all, right? RC is still there, but just getting a RB. Just use a resistor voltage source combination to replace that current source. And they are equivalent circuits. It's doing the same thing. It's providing the same current, the same voltage across the transistor. Okay, more questions, more examples follow. Beta goes to 100. VBE is 0.7 volts at IC is 1 milliamps. So that's the first operating point. So the question is design the circuit so that IC is 2 milliamps, and at that moment VC is 5 volts. So here's the circuit. Oh. So this is not ground anymore. It's minus 15 volts. This is plus 15 volts, and that's RC. So this is RE. And the values for the resistors are not given. Okay. And design the circuit, which means you want to find out RC and REs, right? So when IC is this, you got VC to be this. So for the first condition, for the first operating point, you have a VB, which is 0.7 volts. And at that moment, you got IC, which is 1 milliamps, right? That's what you measured, what you got. And now I'm not changing the circuit, but I want to design the circuit, which means I need the value for the resistors. This is still negative 15 volts. This is RE. And plus 15 volts, RC. And I need this voltage at this node compared to ground, which is 5 volts. And at that moment, the current equals to 2 milliamps. Definitely the VB will be changed because the operating point is being changed already. So VB has to be a different value here. So need the VB first. How? So the only equation connects the VB and IC is this. Right? And unfortunately, we don't know IS. It's not measurable. We just couldn't measure it. We don't know what is that. I know it's a constant, but we don't know for now. So for this case, you have IC is 1 milliamps. You have VBE is 0.7 volts. But you don't know VBE. No, you don't know IS. It seems like you can calculate for IS. Is that necessary? So IC, let's do this. IC1 equals to IS VBE1 over VT. As for the first case, I labeled it as 1, IC1, VBE1. And for this case, I have IC2, IS VBE2 over VT. For here, I know this guy is 1 milliamp. I know this guy, for the second case, is 2 milliamp. And I know here is 0.7 volts. And this is not given. I want to calculate for this guy. So we want to know the VBE2 here. Divide this from this and divide this from this on both sides. This should be equal as well. So what's going to happen is IC1 over IC2 equals to IS over, what's the benefit if you do this kind of division? What's the benefit? This is given, this is given. Cancelled. So you don't have to calculate for IS. It'll save you 2 minutes in your life. And so it's going to be 1 milliamp over 2 milliamp equals to E VBE1 minus VBE2 over VT. VT is given, which is 25 millivolts. All right, plug in the number here, which is 0.7 volts. So you can calculate for VBE2 equals to something. I won't take too much time to calculate this, but is there any questions? No. So you can calculate for VBE2, right? Definitely. So after you get VBE2, what's next? You got VBE here. So it sounds like if I have VBE, I can calculate for everything. Because VBE will determine the operating point. It's going to bias this NPN at a certain point. So the IC will be known and everything will be able to be calculated from here. How? For example, VBE has been calculated. We know VBE2 now. So what is the voltage across VRE? Since we want to calculate for RC and RE. This is asking you to design the circuit so that, right? So these two components are the only two unknown components here. So when you want to design the circuit, you need to tell them what is RC, what is RE. Let's start from RE. So what is RE? Remember, IC is beta times IB, and IE alpha times RE is IC, and also alpha is beta over 1 plus beta, and beta is 1 alpha over 1 minus alpha. So remember these ones. And also IC plus IB is IE. These are the equations you need to know, right? So first, beta is given, and IC is given. Since beta is given, alpha equals to beta over 1 plus beta. So it's going to be this as alpha. And since IC is given, so IE will be alpha IC, which is, no, 1 over alpha IC. Right? And IC is 2 milliamps, so it's going to be 1 over alpha times 2 milliamps. So you can get IE. If we get IE, I want to calculate for RE, but I know IE. How can I get RE? What's the voltage here? Ground. What's the voltage here? I just need a voltage drop across RE. Since I know the current, I just need to know the voltage drop, so I can get the resistance according to Ohm's law, right? Do you know the voltage drop? Do you know the current? Do you know the current first? Do you know the current? Yes, just calculate it, RE. Do you know the voltage drop? Not yet, but can you calculate it? Yes, how? Circuit 1 problem. How? Do you know VBE2? Yes, that was calculated just now. So you just want to calculate what is VE. Find out VE first. And you know VE, you know this voltage, just do a subtraction, you can get the voltage drop. So what is VE? When I'm asking what is VE, is compared to where? Ground. So you know VBE2 is plus minus. So what is VE? What is VE? No. So this is negative 15 compared to the ground, right? And this is ground. And I know the voltage between these two voltages is ground to VE is VBE2, right? You're thinking, hey, you just ground the base. How can I turn it on? You just ground the base. How can I turn it on? It's ridiculous. You just ground the base. You just ground the base. You just give a negative voltage to the E, right? You can still have a plus. Can still have a positive potential drop across based on E, both on emitter. Is this on? Yes, because base is ground, but the emitter is even lower. So VBE is still positive. So what is VE here in this case? What is VE? This is VBE. From here to ground, this is VBE. So when I'm talking about VE, that's from here to ground. So let's make it easier. From ground to here, just forget the letters, okay? From ground to here is VBE2. From here to ground is, hey, yeah, minus VBE2. From A to B is VBE2. From B to A is negative VBE2. Is that making sense? So what is VE? So what is VRE? Positive, negative. What is VRE? VE minus negative 15 volts. So you got a voltage drop across RE. Right? So RE equals to VRE over what? Yeah. Finally, it's got cleared. Right? If you know RE, this resistor is already designed. That's how you design it. You got RE. RE, you can just plug in, grab a resistor from the drawer and plug into the circuit. What about IC? It's way easier than RE. What is IC? 2 milliamps. What is VC? 5 volts. What is RC? Nope. You need the voltage drop. What is voltage here? What is voltage here? Boom, drop. Right? Yeah. So VRC is 15 minus 5, which is 10 volts. So what is RC? 10 volts over what? All right, that's everything for this problem. And unfortunately, you are still not able to do all of the homework problems in the homework tool in that package. But I think only for the last two problems. If you see something involved Q points, just don't do that. I'm gonna cover more on Friday. But that homework 2 is due next Wednesday, I guess. You probably want to start working on that as soon as possible. Just not the last two problems. All right, see you on Friday.